at any time, and I'll be happy to help. It could be about directly the material that I talk about, or it could be about your project. If you think that I can contribute or add any value to it, I'm always happy to help students as much as I can. So I just want to start maybe just with a few inputs from the students to say, what would be some of the take-home messages that you think were important from yesterday? And it doesn't have to be, there's no right or wrong answers. I just want to get some feedback as to what you think we are trying, the message that we're trying to convey, and see if there's anything I can clarify on that part. Does anyone have any, like, what was the heart of what we talked about yesterday? Anyone? Do you want to start? Like, what was the thing, the most, and one of the messages from yesterday?
We have seen principles of green chemistry. I think that reuse is better than recycle. Reuse is better than recycle. We need to take care of the hazardness, and we need to be prepared to deal with. We have to be prepared to deal with the problems before the problems.
Yeah, great. That's great. Good ones. Anyone else? Yeah. Yes, very good. Very good. Anyone else? Yes.
Designing the experience. Not necessarily just designing the process to see a product, but also see what hazards can be generated, or what parts can be more efficient, so less materials, and how green chemistry is more about designing the process.
Yeah.
Understanding of your whole process and not just large scale experiments, but more in large scale, so we can reproduce our ideas, not just in our lab, but also in the society.
Yeah, that's great. That's great. I think, again, there's no wrong answers. I think all of these are so great, but I think that one key word that I think that you said was design, right? I think that's an important aspect of green chemistry, is designing all of these concepts. I think that the 12 principles of green chemistries are not rules to follow, but they're the ways to design your process, right? I think so. Designing things is a very good word. Any other take-home message?
Well, my thought was that prevention is better than control afterwards. That we gotta do everything we can so that afterwards we have to waste time and effort controlling a situation that could have been prevented.
Yes, excellent. Excellent. Very good answer. Anything else? No, these are all really, really, really good answers. So, again, to make sure that you understand the level that you're at, right, at this stage of your careers, is that you all know infinitely more about green chemistry than I did at the same stage of my career. Right? It's like this, when I graduated with my PhD, it was just the beginning of green chemistry. Right? The book had just come out. So before I really thought about green chemistry was many, many, many years later. And so it's just like to say that you, having been exposed to this topic at such an early stage of your career, I think that's a huge step in the right direction. Because then you can start applying these concepts from the beginning, not like me who started in the middle, right? And so the impact that each of you can have based on these concepts is really valuable. And the other thing is that I think that it's you see the different answers to the questions, right? And you see that everybody took something a little bit different from the what we talked about yesterday. And that, I think, is very interesting because it speaks to equity, diversity, and inclusivity, right? Because equity, diversity, and inclusivity is really thinking about problems and allowing many different people with many different viewpoints to contribute to solving problems. Because the way I think about a problem in Canada is very different than the way that you think about solving the same problem in Brazil, right? And having both of us come together to solve problems is going to be, if we're open-minded about it, is going to be the best way to solve problems, right? Because I can contribute something, you can contribute something, but you know what, the way that based on our histories, our backgrounds, our cultures, right? The ways that we solve problems are going to be very different, but all valuable, right? And that's why there's no real, I want to make sure that, like, because it's an overwhelming amount of information that I provide to you, right? So I want to make sure that the point is not to memorize all of this stuff. It's really knowing it, that it's there, and knowing that it's important. And then when you're designing something, then you think, oh yeah, maybe I should access something from the 12 principles to help me with my process that I'm doing here. And that could be, you know, in your academic careers, or it could be if you go into an industry, like, you know, then you'll be able to bring those concepts into industries in Brazil. And that's going to really impact things. You know, once you start impacting industries, you start really making a positive cultural change in your communities, and that's really important. Okay, and again, just stop me at any time if you have any questions or you want me to clarify anything. So, did I turn this off? Oh, don't know why. Yeah. Just to give a couple of examples of the history of some progress in green chemistry. So here's like an example of a dye. And if you think about, you know, the color of kings, like, you know, from a long time ago, purple is associated with the color of kings, right? Because they were the only ones that could afford to have colored clothing, right? Because the purple color was very, very, very expensive and difficult to get from certain plant sources. And that was a dye. And so in 1856, Perkin discovered a vivid purple dye. And that basically opened the door to color being something which was no longer exclusive for royalty, but became generally available for populations, right? And so essentially synthetic dyes was, you know, the progress in terms of color. And then, of course, when one person makes a synthetic dyes, then they open the door to the possibilities of many, many others to come into this and commodify this. And so you ended up with huge amounts of different colors. Essentially, efficiency alone was not enough, but you had to add new value to these dyes, because after a few dozens of years, that essentially all colors of dyes could be produced in relatively low price. And so what was the evolution of these dyes? Well, you know, then this is where chemistry gets involved. And so you have reactive dyes, so dyes that can not only be colored on spools, but could undergo reactions to generate the dyes. In the 1970s, there's thermochromic dyes, so when you apply heat to the dyes, that it can change the color of them. So there's niche applications for that. So essentially, once everyone knows how to make the core product, so this is the original synthetic dyes from 1856, essentially after that, then sustainability and the performance of those materials becomes much more important. And so here's now an example of all of the previous dye examples that we've shown are colored molecules, right? So molecules that have specific colors based on the structure of the molecule, right? So you have to add in, you know, whatever grams of that molecule to make yellow, grams of this molecule to make green, right? So that is a synthetic dye. But so this is where we think about function, right? So the function the importance of the molecule that makes the dye is not the molecule itself. It's the color that the molecule creates, right? And that's the synthetic dye background. But what if we can create color through another process? And butterflies are a great example of this, right? Butterflies, there's no dye in the wings of a butterfly. So butterflies essentially can play blue without using a blue dye, but essentially this is from the nanoscale structure of the dye, and it's the difference in terms of the thickness of the dye that can be used to create different colors. And so that is essentially the varying the fiber thickness of the material in the wings and the structure of those materials, and that's what can color the create the different colors. So now we have multiple technical ways to make colors, and now if we have that, then we can evaluate, can we actually reproduce what a butterfly does in by doing chemistry, physics, photophysics, and create color in a different way. And then the question becomes, which of those processes is going to be more sustainable? Is it more sustainable to make a synthetic dye, or is it more sustainable to make a nanotechnology that is able to vary the fiber thickness and create the different colors? And there's going to be pluses and minuses of each of them, right? Maybe it's going to be easier to make some colors via this process, and other colors are going to be more easily made or more difficult through the dye process, right? But this is just a good example of the end use, right? That's the function of the thing that you're trying to work with is the important thing. It's not necessarily the chemical that is important, but what the function of that chemical is. And so this is just a self-promotion slide, but if anyone's interested. So I'm a co-director of the Center for Nanoscience Research. So I put this in here basically because these are nano materials typically that are used to make these colors in this way. And so we essentially are a group of researchers that are based on nanoscience. So different areas of research you can see here. Nano patterning, we have a large amount of R&D capabilities. So this is all our equipment that we have based in our center. And then we have, we collaborate mostly regionally within the Quebec region, but we do wish to collaborate internationally. So if anyone is doing some nanochemistry, feel free to reach out to us, and we would be happy to talk about potential collaborations. Okay, so green chemistry across different industrial sectors. So again, these are very different industries. So you can have very more commodity industries such as clothing. You could have higher tech industries like electronics. So the green chemistry crosses essentially all of the industrial sectors, and that requires chemists' input to make them more sustainable over time. And then this is just essentially what I said before, but the discussions that go on green chemistry are much more significant than it was even 20 years ago. And this is just an indication of some of the conferences that go on, some of the journals that are focused on green chemistry, and also public education, such as this talk and things like Beyond Benign, that is sort of highlighting all of the key aspects of green chemistry, where we've come from, and some of the challenges that we still have faced going forward. So the future of green chemistry. So again, that word of designing. So it's really the design for hazard reduction. So thinking about the whole process, avoiding high-risk molecular structures. And again, how do we avoid high-risk molecular structures is when we can actually think about them from a chemical perspective and understand why that structure is a high-risk structure, right? It's not only the fact that we can measure the toxicity of a structure, but what we should try to understand is why is there a particular functional group that is causing the toxicity, right? So if we understand molecules, we can understand functional groups. If we can understand functional groups, then maybe an aldehyde will be the toxic part of our molecule, and then we can design around the aldehyde, right? So what is the aldehyde doing in our molecule? Is the aldehyde specifically necessary, or can we use a carboxylic acid, which also has a carbonyl group? So is the carbonyl group important, or is it the carbonyl group of an aldehyde that's important for the function of the material, because it might be toxic because of the aldehyde? And so again, that's where chemistry, a deep understanding of molecular function is really critical. Avoid reduce persistence and exposure. So again, starting to understand some of the issues with persistence and the polyhalogenated molecules that tend to persist in our environments. But again, one thing that I also want to impart on everyone is that scientists are human beings, and human beings can suffer from dogma. So dogma means that we hear something and then we take it as a factual truth forever and ever and ever, right? And that is not great science. So it's important to know dogmas, right? So for example, I'm telling you, polyhalogenated materials are persistent in the environment, but it's important for you to know that that's true, but not take it as dogmatic, because it doesn't mean all polyhalogenated materials are persistent. So the question is that if you want to design a new molecule that's polyhalogenated, most of them have been persistent in the past. So why is yours not going to be persistent, right? And that's the design feature. So it's the fact that you understand the dogmas and the general trends, but you can't accept the general trend as the conclusion, because what we have to do is we have to do experiments to prove if that's true or not true. Right? And that's really important, because I really think that dogma is one of the things that slows progress in any research area, because it gets passed down from generation to generation, and people say, oh, you can't do that. And the next student just says, oh, you can't do that, right? But nobody stops and asks, but why can't we do that, right? That's the important question. If you understand why we can't do that, then you can design better materials or better processes. Again, design products and routes before scale-up locks in risk. So again, it's not our role, because we're not doing industrial chemistry in academia, but it's really our role to sort of start to think about this now, so that we can provide better tools to those who are going to make the larger scale reactions, so that they don't have to re-optimize everything, but they can start from a process which is much more friendly, a green-friendly process from the beginning, and that's going to essentially accelerate the entire discovery process of any design of a new material or new process. So again, I think that this is part of the reason why we like to have these discussions, globally, is that the solutions that are required in every community is going to be different, right? And so that's why giving you the ability to think about these problems is going to allow you to solve the problems that exist here in Lavras and in Brazil, right? Because for someone to come from the outside and solve those problems, it's not going to be trivial for that to happen, right? Because the problems, the nuances of these problems is difficult for somebody to understand from the outside. And so I think that's why it's really giving the tools globally, but then the solutions, I think, should be coming more from the community and locally. And I think, but again, your local solution might impact something in Montreal, right? Because even though your solutions are best solved here, but you might get inspiration from Montreal, and Montreal might get inspiration from Lavras, right? So I think that there is still solutions that could be global, but I think that I think both the solutions, and I think more importantly, the problem, like what is the issues that need to be addressed here, are probably going to be very different than the problems that need to be addressed in where I come from. And that's why I think that it's really important to give these talks around the world. And so so understanding what the function is needed. Can the product be safer by design? can the waste be valuable? So can we take the waste and convert it into something that's economically useful? And then, what role can you play? And I think that the beginning is obviously going to be in your labs, but then afterwards it's going to be going into industries and trying to look for ways that those industries can incorporate some of these concepts of green chemistry into their processes and their design features. So essentially the green chemistry is like changing the way that we focus from the control aspect to the design aspect. So it reduces the hazards and wastes at the source. These design principles are essentially the 12 principles. And so that's the design checklist that we should be looking at to try to optimize any particular process. And essentially, any area of the economy is going to be affected. So health, climate, resources, regulation, cost, innovation is going to be affected by these green chemistry principles. And the future chemical markets will increasingly reward safer and more sustainable design. So we already see this over the last 10 years. There's really been an explosion in green chemistry technologies that have been incorporated, and that comes through government oversight. It can come from consumers who want to be purchasing products that are more environmentally friendly. So there's a large amount of driving force factors right now. And so I think that this is a great opportunity, or a golden opportunity, for us to accelerate the development of green chemical processes. Okay, so that's it for that lecture. Let me switch over to the one. So this is the lecture that I said I would talk yesterday about just my background and my overview. This is my research group last summer. There's my Brazilian, Mariana. She's a PhD student who joined my group. And this was in the defense, the PhD defense of, master's defense of Sarah Taylor, who's back here. So, my path in chemistry, my parents were born in Italy, and I was born in a small city in Ontario, Canada, near Toronto, probably the biggest city that you might recognize. Then I didn't go too far from home, so that's probably the same distance as, it's closer in Belo Horizonte, so maybe half the distance from Belo Horizonte to here. So not far. That's where I did my undergraduate degree in chemistry. Then I went to Ottawa, the capital of Canada, for my PhD, a little bit further away, but probably about the same distance as Belo Horizonte from here. Then I went to Ohio State University. I did a postdoctoral fellowship with Leo Paquette. Then I went back to Canada, to Montreal, Canada, where I was working as a research scientist in Boehringer Ingelheim. And then after, I went to Concordia University, where I'm currently working. So my group works on, so what we do day to day is organic synthesis. So we make molecules. We make small organic molecules. They tend to be aromatic in nature. But what we like to do, and this is partly because of my experience in industry, is that we like to That's weird. What happened? Oh, there we go. So we tend to, I had a friend of mine when I was doing my PhD. He was not an organic chemist. He was a physical chemist. So he was doing a lot of photo measurements of his molecules, so a lot of kinetics. And he would come up to visit me in my research lab, and he would say, it seems like the point of organic chemists is to make little yellow oils and fill up fridges. Right? So we would make a reaction, we would finalize our final compound, we'd characterize it, and then we would take that and we put it in a fridge for some magical day in the future when we think we might need it, but really at the end of your PhD, you're just going to wash all of that into the waste. And so that always struck me, is that we weren't making things with an actual end use in mind, right? We were developing new chemistries without a specific end use. So when I took up the academic position, I sort of thought about that. And so what we try to do more is that even though we're still involved in making those little yellow oils just for the sake of making them because we're trying to develop new chemistries, but we also try to collaborate with a lot of different people. So we have some projects in drug discovery. So we take those molecules and we give them to a biologist and they test them for activity, for anti-cancer activity. We collaborate with physicists, and we look at their optoelectronic properties of some of our molecules. We're involved in green chemistry, so essentially trying to use some of the principles that I've talked about today to improve synthetic processes. And then we have a number of industrial collaborations with pharmaceutical companies mostly, to try to look for ways that we can help them facilitate their research programs. And so the first projects that we work on, and so most of our chemistry involves what is highlighted here in blue. And so these are heteroaromatics, so they're aromatic compounds with at least one heteroatom, usually oxygen, nitrogen, or sulfur. And these are highly seen in drug-like molecules. So here's just 4 examples of drugs that you are actually commercially available, and you see all of them have at least one heteroaromatic ring. And what you'll also note is that usually the heteroaromatic ring is also bound to at least one benzene ring, right? So this is an aryl substituted heteroaromatic, and essentially that bold bond is the bond that we are interested in making. And so just, did I skip a slide? Yeah. So this is our research program in drug discovery. And so this is in collaboration with Professor Elisa Pickney in biology at Concordia. And so we discovered this structure, which has essentially some interesting biology where it's actually disrupting centrosomes in the duplication of cancer cells. So this is an A549 cancer cell that's shown here, and you can see that with the control and then different amounts of our drug, that you can see that we're essentially destroying the ability of this cell to duplicate. And so essentially it also has some selectivity over cancer cells over healthy cells. So that's very important if you're trying to develop a cancer drug. You don't want to kill the healthy cells at the same rate as you kill the unhealthy cells. And essentially what we do is what's called structure-activity relationships. So this is kind of related to what we've talked about in terms of what in green chemistry they call structure-function relationships. So it's this concept of we modify this chemistry, this molecule, we give it to the biologist, they test it for biological activity, and then we see if it's going higher or lower, and then we modify the structure to try to improve the compound. And so we have a compound now that has essentially been improved over this approximately tenfold. So we started something around 500 nanomolar IC50 against triple negative breast cancer, and now it's down to 50 nanomolars, and we probably need to go another tenfold more potent for it to become something which is commercially interesting to a partner. And right now we formed a spin-off company called OncoLeap Therapeutics to try to commercialize this, and we're currently looking for larger pharmaceutical companies to partner with. The materials side of things. So a lot of optoelectronic materials have this common feature. So they have this thiophene ring. The thiophene ring is a 5-membered heteroaromatic with a sulfur. And so here's two sort of advanced materials that have that thiophene ring. There's also other natural products that have heteroaromatics. So here, again, the red is showing the heteroaromatics. And so these are other interesting targets that we focus on. And so to make those, we've worked on things like, and this is a good example of the greening of chemistry. So in 2008, there was a Nobel Prize awarded for palladium catalyzed cross-coupling reactions. Palladium catalyzed cross-coupling reactions essentially are the reaction of aryl. There's a variety of different groups that could be here instead of the hydrogen: boronic acids, tins, boronic acids, tins or stannanes, zincates, organozincates. So what they do is they replace those groups and they do a cross-coupling across this carbon X bond and the carbon metal bond. So in the Suzuki coupling and in the Nobel Prize winning couplings, there's actually a metal here, but you could imagine then you create a bunch of waste, which is the metal X group. And so that waste you have to get rid of because it's a stoichiometric amount of waste. So here, the CH activation that was done, developed by these other researchers, essentially replaced that organometallic species with a hydrogen atom, right? So now the amount of waste that you're generating is significantly lower. So that's a huge improvement. The problem is regioselectivity. So can you get this hydrogen to react selectively over this hydrogen that's on this carbon, right? So when you have molecules that are complex molecules, they have many hydrogens, and to get it selectively one hydrogen over another, it's a little bit challenging. So this chemistry is exceptional in terms of the atom economy of the reaction, but it's not so great because the selectivity can be problematic in certain cases. And so what ways can we get to improve this is that we can, instead of using a boronic acid or organotin, we can use a carboxylic acid. And this is something that my group has been involved in with a number of other groups. And essentially, the byproduct of this reaction is the CO2, which can be captured and reused to make the carboxylic acid again. But here we have sort of an intermediate between the Suzuki coupling, the tin couplings, and the CH activation, because now the carboxylic acid is at a specific place. And because it's at a specific place, the cross-coupling can only occur here and cannot occur where the CH bond is, right? So the regioselectivity is improved. Typically, you have to do a higher amount of temperature to do these reactions. So that's a negative in terms of the greenness of this process. But there is positives over this. So the increased selectivity, but a lot of times you also, in this case, you do not need a co-catalyst. Here you need usually copper or silver as a co-catalyst for these processes. We've also worked on this area, which is desulfonate of couplings. So essentially replacing the carboxylic acid with a sulfonate salt that's shown here. And we get similar selectivity in the sense that we get a cross coupling where the sulfonate occurs, except now we're generating SO2 as the byproduct. SO2 can also be recycled in these processes to generate more of the starting material in a separate process. And so that is, again, sort of the way that we think about things in terms of the circular economy, that you can take the byproduct and try to recover it to make more starting material. And that would be a closed system so that you don't generate waste. Again, really great in theory. We haven't been able to do this super efficiently in a practical sense, but that leaves a lot of room for additional research to occur in these areas. So this is another area where we are very interested in. So the United States Department of Energy in about 2004, they highlighted these compounds that are shown here essentially as future building blocks from biomass, so from sustainable sources. And so this is essentially was a document that was trying to motivate research in new directions to think about the chemistry that we can do with these starting materials, and again, thinking about the function, right? And so what they really thought about in this original document, and I think it was like short-sighted, but it's 2004, so it's very early in the process of thinking about green chemistry, but they were really trying to do like-for-like replacements. So terphthalic acid, I think that, yeah, I have a slide here. So for example, this furan dicarboxylic acid, terphthalic acid is an important monomer in polymer synthesis. And so the fact that you have an aromatic ring and then two carboxylic acids, well, terphthalic acid has an aromatic ring and two carboxylic acids. So they thought of like a like-for-like exchange of these two, right? But they're not thinking about function. So what they're thinking about is molecules. And so they're saying this molecule could replace this molecule, but you have to actually think about, can the function of the polymer behave the same way with these two different monomers, right? So that's where the green chemistry that we've talked about is like making sure that we think about function and not just replacing the molecules because they have the same functional groups, right? The function of the final material. And so even though this is a good idea, I don't think it's practically feasible because the furan is much more unstable than the benzene. And so the polymer that gets made from that would be less robust, but that might be a positive thing because if it's less robust, maybe you can depolymerize it more easily, right? So that's the sort of the overall thought process that you have to think about if you want to incorporate these into your material or whatever you're trying to achieve. But I think that this is kind of an important thought process for everybody in the room, in the sense that if you know that there are lists, and probably as things evolve, these lists are going to evolve, of which chemicals are essentially potential future building blocks, it might be something that you want to incorporate into your research. Because maybe what you're incorporating currently into your research is very cheap because it comes from the petroleum industry. But that byproduct of the petroleum industry, as petroleum becomes more and more scarce, that byproduct of the petroleum industry is going to become more and more expensive. And at some point, that byproduct that you're currently using is going to be replaced by something. You're going to need to replace it with something. And these are some of the things that you should start to think about. And again, it might not be cost efficient now, but we're thinking about long term, right? So you want to be the ones that are developing processes with something which is more sustainable than something that's not sustainable. And so what we took a look at was that HMF was not on this list, but essentially HMF, if you look at the degradation of sugars, HMF is a precursor to FDCA in biomass production. So the HMF that we start with is actually upstream from FDCA, the dicarboxylic acid. So it's actually in the sort of the whole process, it would be considered a likely more inexpensive precursor than FDCA, which I showed on the previous slide. And what we showed was by doing a mechanochemical process, and so I'm going to talk about this maybe on Thursday with one of the last lectures about mechanochemistry. But we've recently gotten really interested in mechanochemistry. So mechanochemistry is, rather than taking what a typical organic chemist does, which is take one starting material and take another starting material, put in a bunch of solvent, and then mix it and then heat it over a period of time. Then you do an extraction to remove that solvent to isolate your final product. Then you usually have to do some sort of chromatography or distillation to purify that organic material. what we're learning is that what we can do, and we're not really learning it, but we're relearning it because this is chemistry that was done thousands of years ago, is that you can just take a mortar and pestle and grind two reagents with respect to one another. And that grinding process creates a lot of energy. And that grinding process might be sufficient energy to get those molecules to react. And now you've done a chemical reaction in the complete absence of solvent, right? And the solvent cost for most organic reactions is the largest cost for the process. So removing solvents completely from the process can have huge impacts on reactivity. Now, mortar and pestle is a relatively primitive way of doing it, but it's a completely mechanochemical way of doing any process. What we do to make it a little bit more systematic, and also so my students don't have to grind all the reactions manually, is that we take pre-made ball millers. And so these are essentially things that either they're steel vessels that you put in little steel balls into those vessels, and it shakes at a very violent speed, and you can control the speed at which it's shaking, and the different speed at which it shakes is going to create different energy. The different amount of balls that you put into the system is going to create different amounts of energy. Whether you put in 1 or 2 or 3, that puts in a different input of energy. You can change the material of the balls from stainless steel to Teflon, so it'll be softer or harder, and that will change the energy input. So you have a lot of controls that you do just like you do in a traditional organic chemistry reaction, but they're different controls, right? And they're different parameters that you play with, but you do this all in the absence of solvent. And so this is really something I found, over the last 10 years, quite remarkable that you can do a lot of these reactions. And so this is one example. So that's where when you see these 3 balls here, that means that we've done it mechanochemically in the absence of the solvent. And what we found is that you can take HMF and you can do a disproportionation reaction. So this is an Cannizzaro reaction. So essentially what you're doing is you're taking one of these molecules to oxidize another one of the molecules. And so you get half of it oxidized to the carboxylic acid, the other half reduced to the alcohol. And again, we showed that you can take this 50% and reoxidize it to the aldehyde and resubject it to these conditions and keep essentially that looped cycle to form this derivative, which has a carboxylic acid on one side and an alcohol on the other side. And what's interesting is that we get complete conversion. So it's essentially complete conversion to this and this. So it's a 50% of each of them. 100%. We are only using KOH in the reaction, so we do have sort of a wasting of one equivalent of KOH, but that's what's required. And the reaction's only 5 minutes, and then we just have to do a workup to isolate the carboxylic acid. And so again, like I said, in terms of the publications, so Green Chemistry is the journal that we published this in because it's a relatively simple reaction, simple process, but the important part of it is the removal of the solvent and the recycling of the materials that you showed here. And so again, every process is not perfect, so we have no solvent required, very small reaction time, no heat has to be entered, but there's always the limitation is that we still can only produce in one cycle 50% of that material. We can never get to 100% because of the nature of the disproportionation of the reaction. We can also scale these reactions up, so we can essentially scale from 100 milligrams to 1,000 milligrams. We have to increase the time a little bit, but essentially we still get relatively good yield. And this is essentially just showing you, in this case, so there's 2 systems that we have. So one is the shaker mill that we call, and then this is an orbital mixer. And so this is the ball miller here. And so essentially it's going round and round like this. And that centrifugal force is what's causing the balls to spin within the system. That's shown here. And that's where you get the grinding effect. And here's sort of an example of the reaction at the start. So we mix everything in the start. And then at the end of the reaction, we have this. And so again, no solvent for the reaction, but this is where, in terms of the green chemistry concepts that we are talking about, is that you have to include the entire process, right? And so if I talk about no solvent for the reaction, what is problematic with what I'm saying? What could be a problem with if I'm saying that this is a solvent-free process? How do I get this stuff out of this jar? Right? That's a question that you need to ask yourself, right? So can you scoop it out when it's like all caked, it's all caked onto the side of the walls of this reaction? That's not trivial to do, right? Because I want to get 100% yield. And so I got to get it all out. But if it's like that, it's really hard for you to think. So what do? You use a solvent, right, to get it out. So now, is it solvent free anymore? So again, this is the thinking about the entire life cycle of a system. And again, we're working towards better improvements, right? So we have solvent-free in the reaction, but we don't have solvent-free in the isolation and in the purification. And so how do you solve that problem? We haven't come up with a good way of solving that problem, right? And so that's an open question that needs to be resolved. There are ways that you can think about this, and this is where collaborating with people in different areas is very important. So polymer chemists have a great way of making polymers, which is a twin screw extrusion. I don't know if you know about this, but you have essentially a screw, you can think about like a screwdriver screwing into a piece of wood. And polymer chemists have little screws where you can actually put in chemicals into the slots of the screw. And then as it's screwing in, the friction is actually causing the polymerization reaction to occur. And they do that in a system where the screw is coming across like that. They're dropping in the chemical like this, and then the chemical is being pushed out the other end, right? And so that's a process that you wouldn't have to worry about taking the material out of the ball miller that we have. The problem with twin screws is that they do it on an industrial scale. There's no lab scale twin screw extruder. So in my lab, I'd have to buy something that works on the kilogram scale, right, to see the proof of concept. And that's something that's not trivial for us to do. So we can't use a twin screw on the scale of our reactions. But if you go industrially, you might be able to solve that problem. But again, that's working with many different scientists, right? Because now it becomes a chemical engineering problem as much as a chemistry problem. The decarboxylative cross-coupling. So again, we are interested in doing these reactions where we can make a carbon bond between a carboxylic acid and an aryl halide. And what we've done is we've made these what are called oligothiophenes. So we keep adding essentially more and more thiophene units. And so P3HT, which is the polymeric version of the thiophene. So if you did this and M, N, and M were in the orders of hundreds, that would be a long polymer. And there's many ways to do that. But as you know, polymers are polydisperse. So when you make a polymer, you say it's a certain molecular weight, but it's actually a mixture of all molecular weights around a single molecular weight, which is the one that is the most common in that polymeric material. So polymers are not uniform chemicals, right? They're a broad range of size of chemicals with all the same repeat units. And so because they have a broad range of size, that means their function could be affected by that broad range of size. And so what we're trying to do is we're trying to say, can we determine what's the minimum number of thiophene units that are required for this molecule to behave like a polymer, right? And that's why we do this as an organic chemist, as a small molecule organic chemist, as opposed to a polymer chemist who's going to make it much more efficiently, but the broad range of molecular weights is going to affect the function of that material. And that's what we're trying to understand, is that the structure function, can we control it better by doing it this way, even though the cost is going to be higher, because the cost of doing this stepwise versus a polymer process is going to be hugely different. This is just giving you for those who may not be organic chemists, but this is essentially irrespective of which project is going on in my group, the thing that my students do on a day-to-day basis is essentially this, right? So this is just one example, is that we're trying to optimize the formation of this bond. What we're doing is we're modifying the catalysts, so we're changing the different types of catalysts, we're changing the ligands, we're changing the bases, we screen for different solvents, time, temperatures, and then what we do is we analyze this. First, we do a workup or extraction, so we remove the material from the organic solvent. We do an analysis, which is typically either 1H-NMR, GCMS, or TLC, and then we do purification of these. So the TLC indicates whether we have that pure or not, and then we characterize it by NMR, proton NMR, carbon-13 NMR, and a high-resolution mass spec. And we determine the percent yield. So this is just an example of reactions that have different outcomes. In this case, it was highly colored. In most of our cases, we don't really have that highly colored materials. Okay, so let's stop there. We'll take a break, 10 minutes, and we'll come back. We'll get back on the green chemistry bandwagon. Okay, welcome back. So I completely forgot to take the microphone off. I hope that it wasn't on the whole time. The funny story is that in Concordia, where I'm the professor, we have the same microphone. And I left it on to go to the bathroom. And so in the room was just the sound of me going to the bathroom, but I was in the bathroom. And then when I came back, everybody was laughing and I didn't know what they were laughing about until I figured it out. So you got to be careful with the microphones. Okay, so any questions or comments? Are we good online? Test, test. It's good. Okay, so we'll go on to, and again, I think that I sent the lecture notes to Teo. Did he circulate them yet? Do you have the lecture notes? No. Okay, maybe. I'll make sure that they get forwarded, so everyone has them. Yeah, so I wanted to just start with another sort of small advertisement. So I'm the co-director of the Center for Nanoscience Research, but I'm also a member of what's called the Center for Green Chemistry and Catalysis. So this is a network of 85 researchers in Quebec. So Quebec is a province of Canada, like Minas is a state in Brazil. So essentially, all the researchers in Minas, all the researchers in Quebec who are interested in green chemistry, we've come together at different universities and we are trying to promote green chemistry research in academics. And so the research axes that we talk about is the invention of catalytic reactions, tools for green synthesis, transformations of renewable resources, and then these two blue axes, which are green chemistry, energy advantage, and evaluation and policy in green chemistry. So again, we're trying to not only do basic research, but we're trying to push different policies in the government to promote green chemistry going forward. And these are the universities that are involved in this. And as I said, we have 85 different research groups that are part of this center. Okay, so today's map, again, you know, there's a lot of repetition in these slides, but I think it's sort of, we're looking at the concepts of green chemistry and we're trying to package them in slightly different ways, because I think that the concepts of the concepts of green chemistry, like the 12 principles that we show over here, can be seen from many different perspectives. And that's why we create the slides in this way. And so what we're trying to do is think about how some of these principles can be gathered with one another. So essentially, if you look at these first 6 principles, they all deal with waste, atoms, hazards, products, solvent, and energy. The remaining principles, feedstock, derivatives, catalysis, analysis, and acid prevention, and how can we compare these different classes of the 12 principles with respect to one another and for particular design problems. So if we look at it in a different way and we categorize them in these types of groupings, so now if we think about it from reducing waste and improving efficiency, well, these 3 of the 12 principles really are dealing with this in particular. And I say this to say that when you are thinking about designing a route, designing a process with green chemistry in mind, that instead of looking at them essentially as 12 individual design concepts, if you look at them under this grouping, you'll more effectively see that if you're trying to reduce waste, essentially probably all 3 of these are going to be applicable. So instead of doing it one by one and you group them, then it becomes a little bit easier to manage which ones to think about particularly with your problem in mind. If you want to reduce hazards, well, you want to have less hazardous synthesis, you want to design safer chemicals, you want inherently safer chemistry, right? So those are all reducing the hazards. Improving life cycle, well, if you have renewable feedstocks, then that improves the life cycle. If you can degrade the final product, that improves the life cycle, right? So those 2 are really designed for life cycle analysis. Improving processes choices, so safer solvents, energy efficiency, catalysis, which essentially is closely related to energy efficiency, and real-time analysis, all are improving the process choices. And so we're going to talk about these in terms of these groupings. So basically, traditional chemistry often manages harm after it has already been created. So we've talked about this before, and what we're trying to do is design out harm from these processes. And so how can we do that? Well, wasteful syntheses require treatment, transport, and disposal. So essentially, inefficient synthesis is going to create a lot of byproducts. It's going to create a lot of solvents. It's going to create a lot of consequences that needs to be dealt with. Reagents and solvents are often selected for performance before hazard. And so what we mean by that is that we think about, as chemists, is that we're looking at a particular transformation and we tend to focus on yield, right? So we change one solvent for another and we say, well, the yield of our reaction has gone from 40% to 90%. And so that's a good thing, right? But that you're looking at a single factor in the whole process design theories, right? So you have to think about the yield, but then you have to think, well, is that solvent that I've chosen for 90% yield, is how easily can we dispose of that solvent versus the solvent at 40% yield? Maybe that solvent is much easier to dispose of, right? So one could be, for example, dichloromethane, and the other one could be water. So that's not a perfect system either, right? And that's again where we think about, well, oh yeah, if we do reactions in water, it should be much safer than an organic chlorinated system. But the problem is that water, you have to then decontaminate it from all the organics that you have in there. So you have to purify that water before it becomes useful again for other processes. So just by doing it in water, that's this thinking of, well, natural is better, right? Dichloromethane is industrial, it's synthetic, water is natural, so it should be better. But we have to look at the whole process. So it doesn't mean that water is not the better choice, but it's more complicated than just saying water is always better than organic solvents. Many products were not designed with degradation or low toxicity as for requirements. I think that's really one of the key issues in these processes. It's not easy that if you, for example, and this is like the 2 contradictory design features that you have in a lot of chemical processes, right? So if you make a polymer for an industrial application, typically you want that polymer to be highly stable, right? You don't want it to degrade under heat, because if I design a polymer for a Canadian application in the winter at -20, I want that polymer to also be useful in Brazil in the summer at +35, right? So the polymer has to be able to, depending on the application, perhaps be equally, the performance of the polymer has to be equal across a large temperature range. And so that means that has to be highly stable across a large temperature range. So then the question becomes, if I want to design it for degradation, then how can I degrade it? I've designed it to be highly stable over a large temperature range, right? So the design feature inherently means it has to be highly stable, which contradicts the degradation ability at the end of the life cycle. So you have to come up with some creative ways to do that. So maybe, for example, you could have something which is light sensitive, right? So maybe for that polymer application is for non-outdoor uses, right? It has to be something which is not exposed to the light, and then maybe you can degrade it by photochemistry. So that could be a design feature that you design into it. So it becomes highly complicated because the function might be contradictory to the degradation process. And how do you deal with that? It's not trivial. And then safety is frequently handled through barriers, personal protection devices, ventilation, and regulation. So again, these are high cost. They have a high human cost because human beings have to deal with these chemicals. So if we can design out things that are unsafe, then we become a much safer workforce, and that is better than having a process that has been designed with highly volatile chemicals that might cause human problems to the people producing it. So thinking about that in the design process can improve things dramatically. So essentially, we think about green chemistry mostly through the lens of environmental protection, but there's a lot of other areas that are affected, are benefited from green chemistry. So, human health through lower exposure and toxicity. And the economy is generally, even though there's usually more upfront costs, but long term, those costs are oftentimes recouped through less waste, lower liability because your employees are not exposed to these toxic compounds in the generation of your materials. Science benefits because we are pushing the boundaries of what can be done with the science and creating new products. And then competitiveness, innovation across sectors. And I think that most governments, this is one of the things that is a key driver to economic performance is innovation, right? So economies that are the most competitive are usually the economies that are the most innovative if you don't have a huge amount of natural resources, right? So natural resources drives economies. The next thing after natural resources is innovation. So if your country has a lot of natural resources, usually you're competitive. If it doesn't, how do you drive your economic growth is through innovation. And that's where, I think that all students should be thinking about, how can I transition the research that I'm doing to become an innovative contributor to the society in which has educated me. Right? And I think that can be really, I think it's something which is underappreciated by graduate students in physical sciences. I think, again, just like I said before, is that I think Brazilian students are competitive globally. I think that the other thing globally that is underappreciated is that graduate students in physical sciences have an exceptional ability to solve problems, solve difficult problems, right? That's what you are great at. Your particular research area that you're involved in, that is a tool, right? That's just a small part of your ability. Your ability is to solve very difficult problems with lots of data input and to produce something of value out of that, right? And that can be applied to so many things, including creating new businesses, new technologies that can benefit your communities. right? So I think that at this stage of your careers, you should really be thinking about that, is beyond just your science that you're doing. I think you should be thinking about, how can I convert this with partners probably, right, to something that could be something economically beneficial. And I think that you have the skill sets to do it. It's just whether you will have the courage to do it. And I think I think it's something that I wish that I would have thought of earlier in my career. And I think that it's not for everybody, right? But it's something that you should at least consider. Essentially, we often talk about hazard, so hazardous chemicals, hazardous materials, but essentially hazard is only one component of risk, and the other component is obviously exposure, right? So risk is essentially hazard times exposure, and so essentially the higher the hazard, the lower the exposure needs to be, and you can still undergo a large amount of risk, or you can have low hazard but huge exposure, and that's going to increase your risk as well. So you need to manage both of those when you're talking about risk. And so essentially what traditionally we've done is we've reduced risk by reducing exposure, right? So we just say that, for example, we get better fume hoods, right? So when you're doing research in a lab, if you have better fume hoods, that means that exposure is going down. But that's not changing the hazards of the chemicals that you're using, right? So your risk is going down because the amount of time that you spend breathing in toxic chemicals has been reduced. But what about if we can reduce the amount of toxic chemicals that you use? Now we're reducing exposure and the hazard, and that's creating a much more safe work environment. And that's just in your lab as a graduate student. You can imagine that if you take that industrially, it's going to have a much huger impact on the workers in those fields. Waste prevention. So we talked about this superficially, but this is one of the take-home equations that you should think about when you think about green chemistry, and this is E factor. So E factor is the kilograms of waste produced over the kilograms of product, right? So the less waste that you can produce and the more product that you can produce per the waste, then the better the process is. And so here, and I think is one of those things where it's this understanding what this means can be very important across different sectors. And so if we take a look at oil refining, right? Oil refining, which we think of, I think is like, if we asked everyone, is that a dirty business or is it a clean business? Right? We would all think of it as a dirty business, right? Oil refining. But the E factor for oil refining is close to zero, right? That's pretty amazing. And so why is that? The kilograms of waste that gets produced per kilogram of product, why is that so low in the petroleum industry? Is because they refine everything, right? It's so valuable that they take every single byproduct that comes out of that process and they commoditize it. So in one way, we're depleting the petroleum that is a finite resource on this earth. And that's a big problem. But maybe we have a lot to learn from the petroleum industry, because what they're doing is essentially that whatever they're taking out, they're making sure they're using everything, right? And so that's actually an industry which for E factor is the most competitive industry. And then if you go to fine chemicals, so things that are more produced, you start to get worse E factors, bulk chemicals, and fine chemicals. Fine chemicals are usually the starting materials that you use in a graduate lab, a graduate school. And then the pharmaceutical industry, then it's even larger, right? Now, of course, we have to take this into consideration, right? The amount of oil that gets produced per year, right? The kilograms of oil versus the kilograms of the pharmaceuticals that get, these are not even on the same scale, right? So a tiny E factor multiplied by billions and billions and billions of crude oil still produces waste, right? Whereas the amount of the pharmaceuticals that gets produced is a small fraction of what the amount of oil. So the E factor is worst, but the total cumulative waste that gets produced is not going to be on the same scale, right? So you have to be careful when you look at these numbers, but it's a good way to measure efficiency within an industry. Right? So I don't think it's fair to compare pharma with oil refining, but within pharma, what you should be doing is aiming for the most efficient process, and the most efficient process is lowering the E factor amount for your process. And I think that one of the most important things is that E factor, essentially, when we do an organic process as a graduate student that I've talked about before, is that like the first thing that you're thinking about is yield, right? So you say 40% and 80%. If it's 40%, we calculate yield in moles, but ultimately what you get out of the product is grams or milligrams or whatever, right? So you get a weighted material at the end. And so 40% or 80% is going to give you, if it's the exact same reaction, is going to give you 100 milligrams, or it's going to give you 40 milligrams if it's, approximately 40% of 100%, right? So what you're doing when you're doing the yield of the reaction is that you're completely ignoring this, right? All you're saying is that how much kilograms of product can I produce? So yield is one measurement that completely ignores a huge amount of process, which is the kilograms of waste. So this is now we have to take into consideration yield, because that gives us some indication of the bottom of this equation, but then we have to factor in waste. And when we factor in both, then we sort of get the real consequence of any process, any chemical process. And so here's just one example that I pulled out of the literature. And so this is sildenafil citrate. And so if we take a look at the process, and again, it's not important for this course, the exact chemistry that's going on here, but essentially what they've done is they've done a 1, 2, 3, 4, 5, 6 step process. And so there's 6 linear steps from something which is commercially available that's shown here to get to the drug material. You see that the reagents that they've chosen here are relatively simple reagents in general. A lot of these steps are crystallizations, so they're not purifying these things by column chromatography on an industrial scale. Silica gel chromatography is essentially not practical when you're doing this on an industrial scale. So a lot of these are recrystallizations for all of these steps, or extractions that's shown here. So this process was the original synthesis industrial process from Pfizer for this molecule. What are some of the factors that might be missing if we're trying to analyze whether this is an efficient process in terms of green chemistry concepts? What are some of the things that could be missing or would be useful to know? So like byproducts? Yeah, exactly. So it's like, what byproducts are being generated and can they be reused? That's a good one. That's missing from here. The solvents used for each step. Yeah. So here they're not indicating the solvent. So that's an important other feature, is that was this done without solvent, which it might have been. But if it's not, then the solvent is definitely something that has to be considered in terms of the efficiency of the process. What about temperature, right? They don't indicate the temperatures here. So did they have to heat these reactions? Did they have to cool these reactions? So if you mix nitric acid and sulfuric acid, that's a highly exothermic process. And so you might have to try to cool that reaction, which is an energy input that needs to be taken into consideration, right? So there's a lot of factors, details that are not necessarily shown here, but it's just to give the highlight of saying it's not only the number of steps, but it's all of these other factors that we have to consider when we look at a process of whether it's a green process or not. And so here, this is essentially the optimized synthesis. So that after the original one, which was good enough to produce the first few years of the product, but they were still trying to reduce the environmental impact and reduce the cost of making the material. And if you see here, they essentially are going to 1, 2, 3, 4 steps. So this is what they call, so the previous example, the synthesis is very linear, right? So every step counts on the previous step. So you're doing it one step at a time. And the second synthesis is what they call a convergent step. So you make 2 different processes, and then you take 2 components that are more advanced, and you couple them together to make a highly advanced final product. And so usually making a convergent synthesis is much more effective than doing a linear synthesis. And so that can reduce the number of steps in the longest linear sequence, and it also can improve the yields of the overall process. And the other thing is that, like, if you look at the yields of these processes, you know, it's 92, 100, 90, 92%. So really high yielding reactions, so that you are getting more of the material into the final product. And a lot of these reactions are highly atom economical. So here you see there is a reduction reaction. So essentially the 2 hydrogen atoms there are the 2 hydrogen atoms that get incorporated into the final product. And so from an atom economy, and we're going to talk about that in a few slides as well. And so they significantly improved the synthesis. Again, it's not critical in terms of the every detail that I show here, but the yield went from 36% in the linear sequence to 75 to 82% in the convergent synthesis. The reaction mass efficiency, so essentially how much of the reactant mass was incorporated into the final product. It improved almost 3-fold, from 10% to almost 30%. And waste intensity, the E factor, was approximately 6, when most pharmaceutical processes have an E factor of between 25 and 100. So that's a significant improvement of the E factor. And this is the amount of solvents that is used for the original synthesis. And this is the amount of solvent used for the new synthesis. So again, huge reduction in the amount of solvent. And so this is an example of the process. So here it's, and this is where I think the pharmaceutical industry is very different than the petroleum industry, is that the function of the final molecule, you can't easily change the final molecule and have the same function. Right? To get another molecule that does the exact same thing as sildenafil is not trivial. And that's a huge cost in terms of research costs. And so here, because the final molecule has to stay the same, the only thing that we can do is this process intensification to optimize all of the ways in which we can actually synthesize the molecule to make it the most efficient. So the function is limited by the end product, but there's still ways that we can improve all of these routes. And in the United States, they have these green chemistry awards that are given out to academics, industries, policymakers every year. And this commercial green process by Pfizer was one of the winners in, I think, about 2010 or so for this award. This is the same as the last slide. So how else can we optimize processes? So we talked about this before too, is that we have process A. We look for the byproducts and the waste, And can we divert those into a separate process, which is B, that could then be converted to some value-added product? So again, this is going to be highly dependent on the industry that you're talking about. This is something which is this whole process, which I was talking about, the petroleum industry. This is what the petroleum industry does very well, because process B can add a whole lot of solvents or raw chemicals that are used for essentially chemical manufacturing, which are the starting materials then for all of our research areas. But the further you get into specialized chemicals like pharmaceuticals, then it becomes more difficult to be able to figure out a way to have a process B which will be commercially viable for using the byproducts of these reactions, because those reactions are just done on such a smaller scale than they're in the petroleum industry that it's harder to find a market for these byproducts. Okay, so atom economy. So this is another important feature. So one is yield, the other one is E factor, and now we have to talk about how many of the atoms of the starting material are incorporated into the atoms of the final product. And so different reactions have different atom economy values. And so if you look at something like the styrene epoxidation, and I'll show you in the next slide what I mean by these reactions. So here I just want you to take-home message is that every type of reaction is going to, or process is going to incorporate more or less of the atoms in the starting material into the product. The less atoms you convert into the product, the more atoms you have to deal with to get rid of, right? So if the atom doesn't go into the product, it's going into a byproduct. And if the byproduct is useful, then that's great. If it's not useful, it's waste and it needs to be dealt with. And so if we look at two reactions, so this is the Diels-Alder reaction. It's a 4+2 cycloaddition reaction between a diene and a dienophile. This is just a simple example to show, but the take-home message is that essentially these 4 carbon atoms and those 2 carbon atoms, all 6 of those carbon atoms are part of the final product, right? So in terms of atom economy, you've economically used every atom in the starting material in the final product. If you look at an epoxidation, again, this is a type of reaction that we learn at, I think, in most undergraduate organic chemistry courses. But if you look at an epoxidation reaction, this is a great reaction. So you take cyclohexene, you epoxidize, you remove the double bond, and you put a carbon-oxygen bond to make this 3-membered ring. It's drawn a little bit funny here, but this is still a 6-membered ring. What you're doing is you're taking this reagent, which is metachloroperbenzoic acid, and you're just essentially peeling off that single oxygen atom, and that single oxygen atom is being attached to this cyclohexene ring. But the waste then is this entire molecule minus that oxygen atom, right? So the molecular weight of the byproduct compared to the molecular weight of your target product is huge, right? The number of atoms here, there's more atoms here than there are in your target molecule, right? So this is a very atom non-economical process. So again, it's a great way to do this reaction if you're doing this in an academic lab. But if you're going to do this industrially, you have to think about all of this waste that you're generating. But this is the type of thing which, if you start to think about it in terms of green chemistry concepts, then it's like, well, how can I do this reaction with a single oxygen atom? Where can I get an oxygen atom that's not part of MCPBA and still react in the same way that that oxygen atom, right? And then that becomes a whole area of research which can involve inorganic chemistry, organometallic chemistry, surface science by immobilizing oxygen on the surface of nanomaterials. right? Because what you're trying to do is essentially trying to replicate something which is atom non-economical with something much more atom economical. And that's the type of problems or the questions that could be answered that could provide great value to the research community going forward. And of course, there are people that have not solved this problem, but have solutions to this problem. I'm showing you a bad example, but there's better epoxidizing agents. But this could be an open question in different areas if you look at it from the atom economy of a process. Less hazardous syntheses. So here's an example of adipic acid. So the synthesis of adipic acid essentially started from benzene-derived feedstocks. So essentially benzenes and all of their derivatives are usually petroleum-based in terms of their origin. And so essentially, because it's starting from the adipic acid synthesis, so the synthesis of this molecule here, starting from this aromatic compound, you have to de-aromatize it to get to the final product at some point. And usually to de-aromatize things, you need to have very strong reactions. So nitration reactions, which generate nitrous oxide as a byproduct and is a potent greenhouse gas. So the alternative is to take advantage of some biochemistry. So now if we think about glucose as a starting material, we can then modify glucose and then take advantage of biocatalytic processes. And so here's an enzyme which can convert this cis muconic acid to adipic acid. And so now we're taking things that are relying on petroleum-based feedstocks. Instead, we're starting with biomass-derived sugars. We're modifying it. We understand that there's enzymes that can do certain catalytic processes very efficiently. So we're starting from biomass. We're using enzymes as part of the process. And so this process ultimately becomes a much greener process because we change the feedstock, we're changing the oxidant, we're changing the solvents because we can use much more water-based solvents here, and we're doing this biocatalytically. So again, this is now thinking about addressing a problem which is coming from petroleum and starting from biomass-based starting materials. So the function of the final material is the same whether it's sourced from petroleum or biomass, but the process is improved significantly because we have incorporated design principles based on green chemistry concepts. Designing safer, less toxic chemicals. So again, this is a real challenge because we need to really dial in what is the hazards that we want to avoid and how is that hazard created based on the molecular structure of the hazardous material, right? So that's where it's the structure-activity relationship, or in this case, the structure-hazard relationship is very important. So we think about carcinogenicity. Oftentimes, carcinogenic molecules are things that can alkylate, for example, DNA. Right? And so if we know that alkylation of DNA is problematic, then we have to look for things that are strongly electrophilic. And if they're strongly electrophilic, then can we dial out the electrophilicity so that it doesn't react with DNA to cause those carcinogenic properties? So again, this is really one of the most challenging features because we're now trying to design structures. We're trying to redesign molecules to have the same function, but it behaves different in terms of the toxicity to a living system, right? So it becomes hugely complicated because the toxicity in a living system is a non-trivial thing to deal with. So I think that this is an area which is widely underexplored because of that complexity. So for example, if you're trying to do something really complex like make a drug for human health, there's great economic incentive to do that, right? Because you can make $1 billion drug. Here, what you're trying to do is change the carcinogenicity of something there's not a huge economic driver for that, because if you change one solvent for the other, you still need a solvent for your process. It's just that solvent is less carcinogenic, but the economic benefit is not the same as making a drug. But all of the processes that you have to understand that compound's behavior in a human being is the same level of understanding, right? And it's very hard to understand how drugs behave in human systems, right? That's non-trivial, and that's part of the reason why drugs, essentially novel drugs, cost so much, because of that process of understanding it biologically. So I think that this is something which is not trivial. I think maybe computational chemistry can have a huge impact on this, because I think that we might be able to learn things through computational chemistry that would speed this process along, because we can understand why the original compounds are toxic, or why they're endocrine activities, and then trying to mimic things that might behave similarly in function, but not similarly in their toxicity. So here's a case study of, for example, DDT, persistent chemicals. So this is essentially, showing that DDT is changing the thickness of eggshells through exposure. So essentially, like things like chickens can't hatch because the eggs are so easily broken, so they can't nest for long enough. And so essentially what we need to do is, deal with things like DDT, because their ecological effects can happen very far from where they are actually exposed. So DDT is accumulating globally, even to this. It's not accumulating anymore, but it's still having effects despite the fact that we stopped using it a long time ago. And so essentially what we need to do is have things that have targeted action and faster degradation, right? So that's where the problem was with DDT, right? Is that we thought about it only in terms of its function, but we didn't think about it in terms of its degradation. And if we can have something which behaves like DDT, so the positive effects of DDT, but degrades in a very shorter time scale, then we would have less of the byproduct, unsafe byproducts of the use of things like DDT. Safer solvents and exposure. So this is, as I said, some areas where I'm working in, which is no solvents. So thinking about doing things in mechanochemistry is something which is very interesting. Water is also an interesting solvent, but again, we have to think carefully about the contamination of water and if we're able to decontaminate it effectively. Supercritical CO2 is an interesting solvent. So essentially condensing down CO2 so that it becomes a liquid. We can do reactions in that liquid, and then essentially you can just release the gas, recapture the CO2, and then do another reaction of CO2. So that's a very interesting way in which we can use CO2, capture it, use it as a solvent, and then recycle it to continue using it as a solvent. The nice thing about that is it's great for purification, because as long as you're not capturing any other gases that are co-eluting with CO2, you can easily recapture and reuse it. These are design options, and so these are not automatic answers, but there's some things to think about in terms of changing more problematic solvents like dichloromethane to things that are going to be safer. And again, this is if you have to use a solvent in any chemical process, usually, and again, you should do this calculation one time when you're doing a chemical reaction, is calculate, because we just calculate the moles of A plus the moles of B, and then we put it in 1 milliliter of solvent. We don't actually calculate the moles of the solvent that we use, because it's not part of the chemical equation reaction that we're doing. But if you calculate the moles of the solvent, you'll see how astonishingly huge that number is compared to the moles of the reagents that you're using. And that's just giving you sort of an indirect way of thinking about solvent being the huge problem in any process, right? Because you're just using so much of it. And if you calculate the solvent that you use for extractions, for purifications, it's really problematic. And so if we can solve that problem, make more safer solvents or remove solvents completely, we're going to have a huge impact on chemical processes. Coffee decaffeination. So I know this region of Brazil is a high coffee producer, but sometimes you want to go to sleep. And so having too much caffeine too late in the day, I don't know about you, but it affects me. It does not affect my wife, but some people like decaffeinated coffee. And so to decaffeinate, organic solvents have been used for the extraction of caffeine, right? And that can be very problematic for a number of reasons. It has a detrimental effect on the processing. You also have to make sure that you get low enough concentration of solvent at the end so that you can use it in commercial applications. And so that's where something like supercritical CO2 has been used to be an effective way to remove caffeine from coffee. So this is, there's been, since this time, a number of different guides, but Amgen has one guide, which is essentially, and so again, it's not important to know exactly what these numbers are, but it's just to say that different solvent systems can be evaluated based on their toxicity, and they can also be essentially co-solvents. So essentially here what they're showing is heptanes mixed with, ethyl acetate plus ethanol, ethyl acetate, isopropanol, MTBE, which is an ether-based solvent, can be mixed in these ratios of these other solvents. And then DCM can be mixed with different ratios of methanol, and they're evaluating them all based on their toxicity. So these are just nice charts to give you an idea of what is considered a more safe solvent system and what's considered a more toxic solvent system. And these are widely available. If you Google them, you can find a whole bunch of different charts like this. And I think it's knowing that these exist can really have an impact on your research, because you can then say to yourself, okay, this solvent that I'm using, is it considered safe or not on an industrial scale? If it's not, then should I be replacing it? And then what these charts do very well is that they actually provide solvents as alternatives that have similar properties to the solvent that you want to be replaced, right? The problem is that the alternatives are not always perfect, right? And there's always a trial and error, but at least you have a starting point to say, if I want to replace a 3% mixture of methanol and MTBE, what are the common ways that industry does that? And I think this is one of the great things that industry is starting to do, is share these best practices so that we understand them better. And again, there's no perfect solution to this, right? So oftentimes in these tables, it will be a little bit more nuanced than what's shown here. So it'll be more like green, yellow, and red. And so the red is the ones to avoid, the green is ideal, but then they still have the yellow ones, which is saying that, there might be some applications where the yellow ones are actually useful. But knowing, for example, DMF, dimethylformamide, is on the red list, and that's one of the solvents that we use all the time in my lab. It makes my group think about, can we replace that? And so we are consistently trying new solvents. Unfortunately, for a lot of our reactions, we have not successfully replaced it, right? So that's an ongoing sort of question in my group, but it's at least we have that always in the back of our mind, is that we want to try to get away from DMF, because we know that it's a problematic solvent that won't be used industrially. I touched on this before in terms of industrial processes. So heating, cooling, separations, and pumping often dominate energy use. And so this is just giving you an energy intensification, so reaction, temperature, contrast. It's just highlighting essentially that things that are at low temperatures, so going below 0 degrees Celsius, these have high energy costs industrially. And so these are the processes that they tend to avoid. Heating is has a high process intensification as well, but not as much as cryogenic. But if you look here, biocatalytic processes, so using enzymes to do reactions, well, enzymes by definition are most effective at body temperature, which is around 37 degrees Celsius, right? So that's a very easy temperature, and oftentimes the enzymes that are designed industrially can be used even at room temperature, right? So they might be more effective at 37, but at room temperature. So biocatalytic processes in terms of the energy that has to be put in is very low compared to doing something at minus 60 degrees Celsius or at plus 100 degrees Celsius. Use of renewable feedstocks. I think this is an under explored area that we are certainly interested in. I think it's partially underexplored. Carbohydrates, I think, has been explored much more than any other area because there's relatively mature chemistry in showing how biomass from carbohydrates can be used industrially. I think that the areas that are quite underexplored is using lignin. So lignin is a very difficult molecule to work with because it's highly polymeric and highly non-uniform in structure. So being able to use that as a starting material towards benzene-derived products, I think is going to be, it's an open question on how that can be done. But if it's solved, I think it can really dramatically push benzene chemistry away from petroleum towards a more renewable and sustainable future. And fats, proteins, and terpenes are also understudied. I think the amount of these that gets produced is so little that it'll be hard to make an economic case at this point, but I think it's still something that we need to be studying for when the time comes where that's going to be more valuable. And the way to think about this is that the same, like to think about E factor and the petroleum industry. So remember that chart where I showed the E factor was nearly zero for the petroleum industry, and it was higher for the fine chemicals and bulk chemicals. Well, this is essentially what is going to happen, have to happen in biomass, because essentially in the petroleum industry, everything was optimized. In biomass, nothing's optimized, right? And so that's why the E factor is huge in bulk chemicals versus in the petroleum industry. And so essentially, that's what we're doing here is we're figuring out how to optimize using these things. And the more we are able to do that, the more biomass, the E factor of biomass is going to become closer and closer to petroleum, to the point where that's where it's going to essentially replace petroleum and let us move on to the next stage of valorization of biomass-based feedstocks. Case studies, renewable and recoverable materials. I think more and more essentially different products are being designed so that they can be reused either in the same target, in the same final product, or being used in
let's say reaction origins. So here's the starting material, here's the product, and you see that without having to wire, it go over this transition state. So the amount of energy that we use within the system is the difference between the energy here and the energy. Right? So that is the transition state energy for any uncapped process. And with the catalyst, what we're trying to do is essentially reduce that energy transition state. So if we can add a catalyst to reduce that, we can reduce the amount of energy that's required. And the importance to keep that.
And in terms of green chemistry, the other important thing about catalysis is that the catalysts can be reused, right? And they're only used in small amounts, right? That's the definition of a catalyst. So the catalyst can be used as little as 0.0001 mole percent sometimes, right? And that means that the amount of material catalysts that you are required for any process is lowering the energy with very minimal amount of material that's required. If it's a heterogeneous catalyst, so it's a solid catalyst, usually those are very easy to recover. If it's a homogeneous catalysis, something that dissolves in your solvent system, becomes a little bit more challenging to recover, but it can still be done, or maybe the cost is low enough that you don't need to recover it because you're using so little of the material. And industrially, what's interesting is that there's some catalytic processes that are done industrially on huge reactors, but those reactors, for example, if they do palladium catalysis, they actually don't even put any palladium into that reactor. They only did it for the very first time, and then the palladium impregnates into the metal cavities, and what they do is they just use that reactor for palladium reactions. And then they don't actually have to add in any palladium because the palladium that's there is always in the metal and it just catalyzes the reaction. The problem is that then you have the use of a resource, which is one reactor for only one type of reaction, right? So you can't use that for many different types of reactions because maybe the other reactions will leach out the palladium from the metal source. But in terms of greenness, that's a very effective way to do things. So catalysis on an industrial scale. So this is HPPO, which is a peroxide, and it's got lower wastewater and energy demand. This engineered enzyme improved selectivity in the process. So for this synthesis and oxidation catalysts, the oxidation catalyst that was used was a bio-inspired one. So it's something from an enzyme, and that enzyme was an oxidation enzyme. And so therefore that enzyme essentially was the inspiration for the oxidation process to produce some of these materials, particularly HPPO, which avoided the use of hydrogen peroxide, which is a toxic byproduct. Design for degradation. So this applies a lot to cleaning products. So a lot of cleaning products became very persistent. And so, 30 years ago, you could see that in wastewaters, there was a lot of foam that was in the, where wastewaters were expelled into, for example, rivers. And essentially that these were caused by different types of sulfonated detergents. And what the companies have done is that they've changed the detergents such that they still are sulfonylated, but they are degraded through the system much faster. So you don't see this foaming anymore. So it's designed degradation of the soap. So the soap works at the in the time frame that's required to clean the clothes, but then afterwards it's designed for degradation. And so you can see that, you know, this is a hugely important factor, because if we don't design for degradation, you know, when we stop something which persists in the environment in 1972, you can see the concentration of that material still in 2025 is still quite significant because of that persistence. So without designed degradation of the materials, you get bioaccumulation that can have long-term health effects. Plasticizers and plastics. And so this is another example where when we make any material, there's oftentimes, you know, the principal material, which is in this case, the polymer. And then there's things that you add to that polymeric material because you want to change the strength or the flexibility of that particular polymer. And so you could either design out a whole new polymer, or you can just start to modify that polymer by adding additives that will change the function of that final polymer. And those additives are essentially what they call plasticizers. And so those plasticizers in terms of design are hugely valuable, but the problem is that they can be leached out of the material. And so the leaching of that material can cause unintended consequences. And so industrially, what they've done is try to put in more plasticizers that are more non-toxic. So for example, using like either derived, having the polymer itself be non-toxic, so something like lactic acid. So polylactic acid is something which can be easily degraded, or using different types of plasticizers that reduce phthalate-related concerns. So removing things like BPA and changing those molecules into something which is less toxic, but still has the same function on the polymeric material. Real-time analysis. So this, you know, I'm an organic chemist, so I tend to focus the green chemistry course mostly on organic chemistry. But again, I think that the real-time analysis is so important, because that can prevent the pollution. It can prevent overuse of energy. If you're not analyzing things in real time and you're only doing it much later than when a reaction is ending or a process is ending, then you are wasting lots of energy, lots of materials, lots of solvent. And so that's why analytical chemistry is really critical to, as a part of the process for improving green chemistry. Process. So here's an example of a process analytical chemistry which enables control. So here's essentially a reaction that is adding on this terp-butyl group onto this ethene molecule. And essentially what they found was that rather than doing this with a liquid acid catalyst, so here, like if you think about this being done in an organic solvent with H+ being the catalyst, by real-time monitoring, they were able to identify that they could have solid acid alkylation. And so this, by GC monitoring, monitored the selectivity of this reaction. And then this is in conjunction with continuous flow chemistry. Essentially, continuous flow chemistry is that you're doing a reaction under a flow. And so essentially what you can do is flow your reagents on top of that solid acid catalyst. And so your reagent is not touching the catalyst for any longer than is necessary to do the reaction. So when you do things in solution under acid catalysis, your reagent, after it reacts, is still in contact with the acid. If you do it in flow, you essentially flow your starting material over the acid catalyst, it reacts, and then it flows out. And so it doesn't touch the acid catalyst for any longer than is required. And so by doing real-time analysis and flow chemistry, they were able to significantly improve this system to make this product that's shown. Inherently safer chemicals. So just a few examples of this is that substituting volatile liquids with solids or low vapor pressure materials is really important. Avoiding large inventories. So we talked about some of the disasters that we talked about at the beginning of last lecture. So these methyl isocyanate vats that were unnecessary. Using continuous flow, which I just said, helps reduce hazardous waste. Simplifying processes so fewer things can fail. So that's reducing the number of steps in any process. PHA, so these are the essentially some of the polymeric materials on airplanes. And so what's interesting about these is that the synthesis is a relatively straightforward synthesis, but it's the fact that that polymeric material, when it's heated, becomes fire resistant. So that's pretty neat in terms of the function of the material, which means that if
Okay, so just to take questions and discussion points and
Tem alguma pergunta?
Let me ask a question. Do you normally have these time slots for lectures? This is normally at 2 o'clock, or it can be any time. Yeah.
trying to connect the chemistry, how this chemistry can help to improve research to achieve more green processes, rather than just use theoretical chemistry to avoid like toxic stuff. And there's the possibility of integrating
Not just using the computational chemistry to try it, but rather, I don't know.
Yeah. Yeah. I mean, are you a computational chemist? Yeah. So like whenever we have lots of computational chemists in our department as well. And when I see their work, like I always think that the challenge is exactly what you're saying, is that how can you do computational chemistry without experimental evidence? You know what I'm saying? So I always am pushing the computational chemists to say, you need to benchmark what you're doing against experiments, because otherwise I don't know what you're calculating. You know what I'm saying? Like, because it's like, they look nice and they create beautiful pictures, but I'm like, but I need to have evidence that what you're calculating translates to a real life experiment. And so I think, to answer your question, there's always going to be, to me, the trial and error of computational, because I don't think you can answer a question without the experimental. But once you have that, then I think you accelerate things tremendously, right? Because once you've benchmarked it, then I'm like, okay, now when you calculate something, then to me, then it's a huge de-risking, right? Because you're saying, okay, here's this. So for example, let's say if you take a process that's a 5-step process and you can calculate a way to make it 2 steps, and you've benchmarked it, and now I have a different process and you calculate and you say, I think I can take your 5-step to 2 steps, then I'm like, it's worth doing. You know what I'm saying? So that's where I feel computational is huge impact. So because it's like, if it can remove the number of experiments that needs to be done, what kind of impact? That's a huge impact, right? Because if I have to do 100 experiments to figure out the solution and you can make me do it in 10, right? I only have to do 10 experiments, the amount of solvent, the amount of waste, the amount of risk, the amount, so it's like, that's incredible amount if you can benchmark it, right? And that's, I think, the key. But I do think that there's, like I said before, is like, structure toxicity, I think, is something which is very difficult and nobody wants to do it because structure activity can make me make $1 billion drug, and pharmaceutical companies invest huge amounts into that. But structure toxicity is kind of like, you know, the thing nobody wants to do because it's decreasing the cost. It's not introducing a new drug into the market. And I think that computational, to me, could have a huge impact in that area because that area is like something which people would be more willing to sort of experiment with non-benchmarked studies. Because if you can at least point me in the direction of alternatives, I think that it would be a huge impact. So I don't know if that answers your question, but
Can I say that computational tools is a green tool and one strategy to improve the sustainability of process?
yeah, I mean, so how much energy is used when you do computational studies, right? So it's like, it's one of those things where I know what you're saying and I agree with what you're saying, but I'm just saying that there's not a zero cost. You know what I'm saying? So it's like a little bit like, and again, I get called out on this all the time with my experiments because with my science, because I'm like, it's not green, right? Because I use some terrible solvents. I have to do things at 150 degrees. So, you know, so it's just, I think that the way to think about it is that exactly like you're thinking is that computational is it is, if it can reduce the number of experiments, it's pushing things in the right direction. But everything comes with a cost. So that's why I'm just like, I don't like to ever say like, you know, this is green and this is not, right? It's like, there's nothing that's perfect. I think that we just need to become complete. We just push things in the good direction. And if we're always thinking about it, we can continue to improve, and that's all we can really hope for, ultimately.
I think it's because one of our justificatives for some of our work and research are just the idea that with computational tools we can use less solvents, less process, and better direct.
Yeah. And that, like, and again, there's just make sure that to be clear, is I don't want to prevent you from saying that. You know what I'm saying? Because it's like there's two different things going on. One is we're just philosophically talking about green chemistry. And I want everyone to come away from this to say that good and bad is too simple. But then what you're talking about is trying to get a grant or to publish a paper. And to do that, you sell your science in the most positive light. You know what I'm saying? And it's like you can't be so transparent that if you're so honest, then it becomes, the reviewers say it's not so interesting, right? So then it's not that you hide, but you only highlight the positives. And I think that you're absolutely right. Green chemistry is like, you know, theoretically, if you can calculate everything, if your computation was so good that you could predict, like, you know, everything 100%, and I only had to go to the lab and do one experiment, I mean, of course, like that's the ideal world, right? Like for sure that would be much greener than what we do right now, which is just, you know, this trial and error experimentally. Yeah, I mean, you know, AI is like, you know, one of those things which is, it's underestimated what we're doing globally in terms of the energy consumption. And I use AI all the time, right? But it's one of those things where you should think about, should I be using AI when I could probably Google it, and the amount of energy that would be used from a Google search is going to be a fraction of what the AI searches. Tough questions, right?
And a lot of water costs.
Water costs, exactly. These are like I said, economists call negative externalities, right? Society is paying for my AI search, right? And it's not being paid for by me, who's doing the search. And it's like, we need to think about those things. It's like the people who are doing the searching, if I had to pay $100 because that's the true cost to society every time I do an AI search, I would think twice about doing the search, right?
I would like to try a little bit.
Yeah.
I'm thinking about is ever good to try to enjoy in a really green bottle. I'm thinking about I'm starting to go and I don't really know if the results will go good or bad, if this project will work or not. And is it good to try to think this entire project in a green bottle?
Yeah, I mean, that's a really good question, and it's a tough one, right? Because if you're doing a graduate studies and you want to succeed, and so are you going to essentially limit your options to these green chemical principles to succeed? I mean, I think that the answer is yes, right? We have to start doing that. So it's not that you are, you can't see it as limiting your options. It's just that you're making better design choices based on these principles. And the success, I think, is likely to be the same but different. I think you just have a little bit, the challenge becomes that the history that we know that is non-green chemistry, quote unquote, is just, we have a larger amount of knowledge about that. The green chemistry knowledge that we have is a little bit more limited, but I think it's limited in terms of our, the history of us thinking about it, but I think it's unlimited in terms of its potential. So I think in that way, you have a lot more ability to discover something which is not known, right? Whereas if you continue to do things which are, quote unquote, non-green, then you're likely to find something which is already known, because there's been so much research done in that, with that mentality, right? So I understand the hesitation to want to do it, but I do think that there's more opportunities ultimately, and ultimately it's like more positive.
I think that my intention is set to think about it and then try to get more really bad.
Yeah, but like, and again, just because of my history in terms of my research program, I think that that's exactly my problem right now, because we designed chemistry without thinking about green chemistry. And then we're now stuck because it's like, research is like the branches of a tree, right? There's so many different paths that we can go down. But then what we can do is that if we've gone down a path not that far, we can go back up and go down another branch. But sometimes when you've gone down so far down a branch, you're like, you don't want to go all the way back up to the top of that tree to go down another branch. And I think that that's the thing with my chemistry, is that we designed it so efficiently for using DMF as a solvent. Now we're trying to get rid of DMF, and we're so deep here that we can't get out of it. And that's why we're so stuck with DMF. Whereas if we would have, from the beginning, said we're not using DMF, I think we would have went down another tree and we would have succeeded, right? But it's just like, because going down the other tree is like, it's not as simple as just removing DMF. It's because we have a palladium catalyst, we have a ligand, we have an additive, and those things have all been optimized for DMF. And so now we're just trying to pull out DMF and pull in something else, but all the other things need DMF, right? So we have to redo everything. And It's just like that becomes much more challenging. Not more, yeah, I mean more challenging, but it's more time intensive. And now my group just like it's just human nature. We don't want to do that because we know this works, right? So it's like to get anyone to go all the way over that hump to get to the same thing that we're doing here. You know what I'm saying? Like that's the problem, right? It's like you go all the way over here to get an 80% yield of the same reaction that we're doing over here. So then it's just like, well, let's just keep using DMF, right? Who cares? Well, society cares.
Possibility, but that's something that is likely right now. Well, you have to do is you need to get a product, but you have two possibilities of reacting. One is extremely toxic, but it's I don't know 100% product, and one that is more easy. It's not toxic, but it use smaller percentage products. So if the reactant is very toxic, but it's totally consumed and it's 100% of the product. Would it be green or not?
Yeah, I mean, it's complicated, right? It's like, is it green? It's like, so you're changing the risk profile, right? So the risk for that example, you're putting onto maybe, let's say, the employees who are producing the material, right? Because they're the only ones that are going to be exposed to the toxic material. So, you know, then it's like, is that a risk that you're willing to take? But because the final product to the consumer has zero toxicity and the cost to society is better because your atom economy is perfect because all of that toxic material gets converted. So, you know, that's like sort of an example of like nothing's perfect, right? So maybe that would be acceptable. Maybe the risk to those people it's unacceptable. And then the cost has to go to society, which is to the less efficient route, but the safer for those people. Complicated questions.
And you brought us the possibility of using biomechanisms. I would like to know if it is applicable right now in large states industry, and if it is, how do they deal with it? Because I think we use also proteins, and how do they do that in a industrial state?
Yeah, so it certainly is done industrially by pharmaceutical industry, even other chemical industries. And yeah, it's like there's processes to make these proteins or whatever enzymes that they're using on an industrial scale. So I'm certainly not an expert on it, but it's like it is done industrially. Yeah, and it's becoming increasingly more. It's being done even more and more as time goes on. Companies are finding it quite useful for specific transformations.
And Axios is based on Canada, or do you have people that work for you?
Yeah, so there's an office in Brazil and there's an office in Canada. So the office in Brazil is just sales, and the research office is in Canada. Yeah.
What's the Axios provide?
So we make reference standards for the generic pharmaceutical industry. So like we make. So when a generic company has to make the equivalent of a pharmaceutical that has previously been made by a big pharmaceutical company, they have to make sure that their formulation matches the formulation of the big pharma. And so they have, you know, in their synthesis route, there's byproducts. And so they have to characterize those byproducts to make sure that they're low enough concentration that matches or exceeds the previous synthesis. So we provide them those byproducts, and those byproducts then they use to test. So these are essentially analytical testing molecules, but we make them through organic synthesis. And like, I mean, the biggest company that I know that we deal with is Brain Pharma. I don't know if anyone knows, that's a generic company, a apparently a big generic company in Brazil. Okay, that's good. So we'll see everyone tomorrow. Oh, I was gonna send a little PDF or something to circulate, which you maybe, if you're interested, I won't force anyone to do it, but you can fill in like your research area, your research topic, and like it just has some questions in terms of green chemistry. And if you want, like, you know, to make a few slides on PowerPoint that you can present, then we can sort of discuss your research area and how we think that we might be able to focus it towards green chemistry based on the concepts. So, like I said, I'll share it with you, and if you're interested, fill it out. We can do it tomorrow. And if no one's interested, that's no problem too. I don't want to make anyone feel uncomfortable. I think it would be an interesting exercise. Okay, see everyone tomorrow.